Today, we are going to master the art of counting possibilities. And look, I know that might sound a little nerdy, but it's a skill that pops up everywhere, from figuring out probabilities to just planning your day. By the end of this, you'll see the simple logic that divides pretty much every counting problem into one of two camps. It all really starts with a simple question. Think about it. When you're arranging books on a shelf, the order matters, right? But when you're piling toppings on a pizza, do you really care if the mushrooms went on before the pepperoni? Probably not. This simple difference between caring about the order and just caring about the selection, that's the key to everything we're about to cover. All right, first step. Let's step into a world where position is everything. This is the world of strict rules, of sequences, and specific, meaningful placements. And the official name for this is a permutation. The definition here is perfect. It's all about arrangements where the order is, and I quote, highly significant. The two words you really need to lock in are arrangement and order. If you swap two items around and it creates a genuinely different outcome, you know you're dealing with a permutation. Now, don't let this formula on the slide scare you off. It's just a tool we use to make the counting easier. N is simply the total number of things you have to choose from, and R is how many of them you're actually picking and arranging. Think of it as just a neat little shortcut for counting all those ordered possibilities. So let's make this real. Here's a question for you. You've got 4 different letters, M, A, T, and H. How many different ways can you line them up? Just take a second and think about it. We can actually solve this with just plain old logic, one spot at a time. For that first position in our lineup, we have 4 choices, right? M, A, T, or H. Okay, let's say we pick one, say M. Now how many letters are left for the second spot? Well, only 3. Then you've got 2 for the third spot, and finally, just one lonely choice for that last position. And to get the grand total number of arrangements, all we have to do is multiply those choices together. 4 times 3 times 2 times 1, which gets us to 24. And in math, that's also known as 4 factorial. And that, my friends, is the answer to our permutation problem. And this is where we see permutations out in the wild. Think about assigning specific roles like president, VP, and secretary. That's a permutation because it matters who gets which title. A padlock sequence? Oh, for sure. 1, 2, 3 is definitely not the same as 3, 2, 1. Awarding medals, arranging books. In all these cases, the order is absolutely everything. Okay, so that's the world of strict order. But what happens when the order doesn't matter at all? Now we're entering a much more relaxed world. We don't care about the arrangement or the sequence. We just care about what ends up in the final group. And this is called a combination. And again, this definition is spot on. It's the selection of items where the sequence or positioning is irrelevant. The outcome is just the group itself, not the order in which you picked the members. And here's the formula for combinations. Now what's really cool is how similar it looks to the one for permutations. But look closely. See that extra R in the denominator? That little addition isn't just for show. That's the secret sauce. It's the part of the formula that divides out all the duplicate arrangements of the exact same group. It's how we go from counting every possible lineup to counting just the unique groups. So where do we see this? Well, think about selecting a committee of 3 people. Does it matter who was picked first, second, or third? No way. The committee is the same group of people. Choosing your pizza toppings, picking flavors for an ice cream cone, or just forming a cleanup crew. These are all combinations, because the final group is what counts, not how you got there. All right, it's time for the ultimate showdown. Let's put these two ideas side by side to make absolutely sure the difference is locked in for good. So if you remember one thing today, let it be this. Permutation is all about arrangement. When you see keywords like order, sequence, or positions, your brain should be screaming permutation. On the flip side, combination is all about selection. If you see words like choose, select, or group, you're almost definitely dealing with a combination. This table just makes it crystal clear.
For task X, we need to fill specific ordered roles. That's a permutation, no question. But for task Y, we're just forming a general team. The order is totally irrelevant, so it's a combination. It's the same number of students, but the goal completely changes the math.
Okay, this leads to a really important question. If you're picking, say, 3 items from a group of 10, why are you always going to find way more possible permutations than combinations? And here is the answer. This is the big aha moment. A combination is just one group. Let's say the group is Anna, Ben, and Chloe. That's one single combination. But permutations? Oh, permutations have to count every single way to arrange that one group. Anna, Ben, Chloe. Anna, Chloe, Ben. Ben, Anna, Chloe. You get the idea. As the slide says, permutations count every unique lineup for every single group.
Now let's have some fun and see how we can use these two ideas together to solve problems that are a little more complex.
All right, here's a classic multi-part problem. We've got 2 different groups, red balls and blue balls, and we need to make selections from each of them. Now notice that keyword choose. Right away, that should tell you we're in the world of combinations.
So we just break it down. First, let's figure out how many ways we can choose 2 red balls from the 5 that are available. That's a combination, C of 5, 2, which works out to 10. Next, how many ways can we choose 1 blue ball from the 3 available? That's C of 3, 1, which is just 3. Now, since we need to choose the red balls and the blue ball, we use what's called the multiplication principle. We just multiply our results. 10 times 3 gives us 30 total ways.
So why does getting good at this counting stuff matter so much? Well, it's because it's the absolute foundation for understanding the entire world of probability and chance. When we talk about probability, the first thing we need to know is the sample space. It sounds like a fancy term, but it's just the set of all the possible things that could happen. For a single die roll, the sample space is just the numbers 1, 2, 3, 4, 5, and 6. It's the entire universe of possibilities we're working with. An event is the specific thing you're hoping for inside that universe. So for example, your event could be rolling an even number. In that case, the outcomes you want are 2, 4, 6. At its heart, probability is simply the number of outcomes in your event divided by the total number of outcomes in the sample space. And that's why counting is so fundamental. So as we wrap up, I'll leave you with this question. Think about your daily life. When you're setting a new code, figuring out a schedule, or just picking out lunch. Are you dealing with an ordered permutation, or is it just a simple combination? Once you learn to spot the difference, I promise you are going to start seeing the math of possibilities absolutely everywhere.